Welcome back to Logical Thinking, and today we're going to be talking about logical connectives and truth tables. Now, logical connectives are ways we can combine propositions or binary signals in a way to make more advanced propositions. And often when we use these connectives, we're going to use the propositions as variables, which could be true or false. Once we have this, we can create what we call a truth table. And one of the nice things about this is whenever we combine propositions with connectives, we get new kind of more complex propositions. And likewise, we can take compound or complex propositions that are joined by connectives and break them down into smaller pieces until we get basic or atomic propositions. So I'll show you what the most common connectives are, and then I'll give you an example of each, including what it's called, what it means, and how it's displayed in a digital circuit. And I find it helpful to be able to go back and forth between the circuit diagram version and the sort of logical algebraic way. It kind of just may help you, especially if you're more a visual learner, to see the circuit diagram, but to also be able to write it in terms of the algebra. If you consider these connectives to be building blocks like Legos, which can be snapped together, we can consider all of these connectives to kind of be like this thing where you put in propositions and you get an overall combined statement that's a new proposition that has its own truth value. And what can help here is drawing what's called a truth table, which is something that describes the relationship between the truth of the inputs or these individual propositions and the truth of the output. So we start by writing the truth table of each input variable, if you will, and this example is going to be A and B. We need to cover all possible combinations of inputs and outputs, so we're going to need 4 rows in our table, 2 for each of the possible values of A, because A can be true or false, and for each value of B, it has 2 values that correspond to each of the 2 values of A. So we're going to have 2 times 2, or 4 rows in our table. And from here, what we have is, if I know what the truth values of A and B are, I can just simply look up the row in the table and find out what the value of the output are. Now, these logical connectives, such as conjunction, which you see here, are actually defined by their truth table, how they respond when the inputs are true or false. And the nice thing about this is this gives us a full description of what's going to happen when we know what the inputs are. So that's why it's important to write out all possible combinations of the inputs and outputs. So now what I'm going to do is go through each connective and talk about it. The first connective we're going to talk about is what's called a unary operator. Unary coming from un or uno, meaning one. And it's called this because it just operates on a single proposition to give a new proposition. And this one is called the identity, and it's just basically written as, C equals A. And it really doesn't do anything to it. It just kind of copies the truth value of the output to the input. And you don't see this too much in like logic because it doesn't really do anything. But in digital logic, we often call this a buffer, and it's written as this little triangle in the top right. And the reason for this is we use these when we need to buffer the output from the input, meaning protecting it from noise or perhaps amplifying the signal. Even though in logic we say things are either on or off, sometimes the logic level voltage needs to be boosted due to some voltage loss across a wire. So this is the difference between understanding the logic of your circuit and then, what happens in the real world. It's good to be able to understand, okay, if things aren't working, is it because I implemented the logic wrong, or there's some other physical problems with what I'm building? It's important to know that. So this identity here, once again, logically it doesn't do anything, but you may see buffers in a circuit, and its truth table is just the same as the input. So it basically just mirrors whatever the input is doing. The next connective, and really the first interesting one, is a unary operator called negation. It is written as not A, with either this rectangular hook thing or a line above it. And in computer programming languages, you'll often see the tilde in front of it or an exclamation point. That's how you see it often in C or Verilog, like hardware description languages like Verilog. And that's how it's represented. But when you see logicians use it, you'll often see this rectangular hook thing. And digital logic, its negation is called an inverter because it inverts the truth value of the input. And in a circuit diagram, it's like a buffer with a little dot or a bubble at the end. And whenever you see this little bubble, you just convert this to an inverter or a negation. You just flip the truth value around. So it's like opposite day when it comes to negation. What is true is now false, and what is false is now true. And since there are only 2 options, there's really nothing else it can do. So for example, let C be the claim that Tatsu has a big pretzel loop. The negation of this claim, or not C, is like saying Tatsu does not have a big pretzel loop, or it is false that Tatsu has a big pretzel loop. And one of the things that's important to note is you can negate a negated claim. And in this case, the negatives cancel out. I mean, think what would happen here with the truth table. You'd be back to your original claim. So this would be like saying, it is not the case that Tatsu does not have a big pretzel loop, or, it is false that Tatsu does not have a big pretzel loop, where the negatives cancel, and this is the same thing as saying Tatsu does not have a big pretzel loop. So think about, multiplying a negative number by a negative, you get a positive. It's the same idea here. Now we're going to move on to what are called binary operators. binary from bi meaning two, because these operate on two propositions to give a new proposition. The first one we're going to talk about is conjunction or logical and. It's written as A and B, either with this large caret or with the ampersand sign. The ampersand sign, once again, which you see on the right, more common in computer science, computer programming languages like C, or hardware description languages like Verilog. And on the left, this is what philosophers and logicians may use. And in circuits, the AND gate is written as this rounded D-shaped thing. So it has a flat end where the inputs come in and then a rounded end where the outputs go. And the truth table of A and B is it's true if both the inputs are true and it's false otherwise. So this is why we say and. It's true only if A and B are true and false otherwise. So for example, let A be the claim that X2 is a wing coaster and B be the claim that Gatekeeper is a wing coaster. The conclusion C, which is A and B, is true only if both X2 and Gatekeeper are wing coasters, which in this case is true. So if one of them was not, then saying both X2 and Gatekeeper are wing coasters would be false. The next connective we're going to talk about is disjunction or logical or. It is a binary operator written as A or B with a downward facing caret, or with this little line in between. This is, shift plus the backslash symbol on your keyboard. And one of the ways you can remember which direction the caret faces for conjunction versus disjunction is to remember that conjunction is the same thing as logical and, which starts with an A. So the caret looks like an A without the little line in between, and that looks like the caret for conjunction. And for disjunction, a dis is like putting someone down, so disjunction has the sort of downward facing caret or arrow. That's just kind of how I remember it. Now in circuits, the OR gate is written with this little arrow-like shape. You can notice that the back isn't flat like and it has the following truth table. Basically, it says A or B is true when A is true, or B is true, or both, meaning it is only false when A and B are both false. Now, one point of confusion here is in English, sometimes when we say or, we may mean exclusive or. So if I was ordering food at a restaurant and the waitress says, do you want fries or onion rings? I may not be able to say, oh, I'll take both fries and onion rings. But when it comes to logical or is true if both A and B are true as well. So it's not exclusive. So for example, let A be the proposition that I will ride Maverick and B be the proposition that I will ride Steel Vengeance. C being A or B is true if I ride either one or both of them. So it's false only when both are false. And as an aside, if you go to Cedar Point, you really should ride both of them. But this claim would be true if either one or both are true. The next connective we're going to talk about is exclusive or sometimes called XOR. This is a binary operator that's perhaps a little bit more like the English use of the word or, meaning it's true when A or B are true, but it's false if both are true and false if both are false. And this is more like when the waitress asks if you want fries or onion rings and you can't choose both. This is written as A with this little plus thing in the circle, or A caret B, but this is the small caret, shift and 6 on your keyboard. So this caret notation, once again, very common in C and your programming languages, and this circle with the plus in it is more common in logic. The XOR gate in circuit logic, it looks like an OR gate, but with an extra line on the back, I guess, to show the exclusivity. So when you see that line behind the inputs on the OR gate, that means it's an exclusive OR gate. So for example, let A be the proposition that I go to Six Flags Magic Mountain on Wednesday, and B be the proposition that I go to Cedar Point on Wednesday. A, X, or B is true if I go to either of them. It's going to be false if I visit neither park, and it would also be false if I found some way of going to Magic Mountain and then taking a flight and also going to Cedar Point. So really, this one is true when the inputs differ, and it's false when the inputs are the same. The next connective we're going to talk about is the conditional or material conditional. This is a binary operator that is sort of like the conditional notion of if and then, but it has a bit of a subtlety that makes it confusing for some people. So A implies B is false only when A is true but B is false. So in this case, the order of A and B does matter, and it's true everywhere else. So here's the truth table, and let's consider a simple example. Let A be the proposition that the winds are more than 5 miles per hour, and B be the proposition that Project 305 is closed. A implies B is true whenever A and B are both true. So if the winds are more than 5 miles per hour and Project 305 is closed, meaning they're both true, then A implies B is going to be true. And this makes sense. A implies B is false when A is true, but B is false. And this also makes sense. If I claim that Project 305 will be closed if the winds are more than 5 miles per hour, the winds are more than 5 miles per hour, but Project 305 is open, then I've kind of created a contradiction here. What happens if the winds are less than 5 miles per hour? Well, in this case, the conditional doesn't really kick in in because it really just says if A is true, then B will also be true. But what happens when the winds are less than 5 miles per hour? Well, there are several options. It could be the case that Project 305 would have been closed if the winds were more than 5 miles per hour, but we don't know that because this isn't the case. Or it could be the case that, say, the winds are less than 5 miles per hour, but Project 305 is closed for some entirely other reason, because maybe it needs a new wheel or something. And this is a case where we say A implies B is vacuously true. This is why I mark it with the asterisk there on the truth table. When the antecedent, meaning the first part, in this case A, is false, we just say that A implies B is trivially true. This doesn't quite line up with our intuitions in English because what we often mean in English is, what could have been if A was true. However, these notions of logic don't capture this distinction, and to do that you would need something called modal logic, which talks about possible worlds. And in fact, this is why some logicians put the word material in front of the word conditional, so we don't get confused about cause and effect. A implies B doesn't necessarily say anything about A causing B, it just says B is true whenever A is, so it's about logical relationship. So if A is not true, then B is sort of off the hook, and for all we know, B could be true if A was. So as a result, we're going to give it a value of true whenever A is false, because we don't want to penalize A implies B for something that didn't happen. I have another video on the material conditional that explains this in a bit more detail and why it takes this particular form if you're interested, but for now you may just want to commit it to memory that A implies B is false whenever B is false and A is true, and otherwise it's true everywhere else. And there's no explicit circuit diagram for this, but you can write it by just saying not A or B. The last connective we're going to talk about is the biconditional. This is a binary operator that says A is true if and only if B is true. And it has the following truth table, and it's often written as this double-sided arrow. When we say it out loud, it's often A if and only if B. And one way to show this is to show that A implies B and B implies A. So if you can establish it both sides, you can show that this is true. And what this actually ends up doing is showing that A and B are logically equivalent because it's true whenever A and B have the same truth value and false when they differ. Now think about how this is related to another logical connective we talked about. You can pause the video and think about it if you want, and I'll give you the answer in a second. But for now, let's consider an example. Let A be the proposition that I will go to Six Flags Great Adventure, and B be the proposition that El Toro is open. Saying C equals A implies B is like saying I will only go to Six Flags Great Adventure if El Toro is open, and El Toro will only be open if I go to Six Flags Great Adventure. The circuit diagram for this biconditional is called an XNOR, which is an XOR or exclusive OR with an inverter at the end. Remember that little bubble means invert the signal. And recall that the exclusive OR is true only when the truth values of A and B differ, meaning one is true and the other is not. And XNOR is true when they do not differ, which means A and B have to both be true or both be false for XNOR to be true. And this is why we say the biconditional captures logical equivalence, because it basically says, does A and B have the same truth value? So basically, this would be false if, say, I didn't go to Six Flags Great Adventure, but El Toro was open. Or it would be false if I went to Six Flags Great Adventure and El Toro was closed. One of the nice things we can do here is combine propositions in different ways, which actually kind of nests them together. And in circuit diagrams, this is often like plugging in the output of different circuits into the inputs of others, or kind of wiring up in a way where the output of one gate goes into the input of another. In this case, we often, when we write it with algebra, use parentheses to show the order of operations. Both the circuit diagram and the text above refer to the same logical function, and both actually have the same truth table. And when creating a truth table for these, it often helps to start from the inside out, or from left to right. So just like algebra, we're going to start with the innermost group, compute the truth table as we did, and sort of add more stuff. So let's just let x1 be not A. So what I can do then is just substitute x1 in. So now I have the overall statement Z being equal to x1 and B or C. And then what I can do is let x2 stand in for x1 and B and compute the truth table for x2. And from here, then I can say, well, Z is just x2 or C, so I can compute the truth table of that. So if you compute the truth table for these intermediate values, you can just substitute it in, and it helps break the problem down. But once again, it helps to start with the innermost value. So just as we did for XOR and XNOR, we can add an inverter or negation to the end of each of these gates to get inverted versions of them. So one example would be NAND. We can take AND and NOT to get NAND or not and it's just really adding an inverter to the AND A and B. So this is actually false when A and B are both true and true otherwise. And similarly, we can add OR plus an inverter or a NOT to get NOR or not OR. And it has the truth table that is true when both of them are false and false otherwise. Thanks for watching. In the next video, what I'm going to do is talk about the 3 laws of thought, and then we'll get into logical arguments.